So we're coming down to the end. We haven't had any kind of Internet of Things talks in this track before, so I'm kind of excited to hear about this. We're going to hear about speedometers, right? Sorry, we're talking about speedometers and things that you can put onto your bike. This is going to be really cool. Let's give our next speaker a big round of applause. Have a good time. Thank you.
Hi, everybody. Thank you for being here on a Sunday afternoon. I'm Toma. I'm from Hungary, and I work for a small IT security company as a pen tester developer, the company called PR Audit. I'm a regular speaker at Hacktivity, Central Europe's biggest hacker convention, and I also gave a talk about insecure game scripting engines last year here at DEF CON. So the title of my talk is Help, I've Got Ants. What are we doing with the ants? Last year I've targeted one of my hobbies, flight simulators, so I thought it would be appropriate to target one of my other hobbies this year, mountain biking. And while creating this slide, I've just realized that all of my hobbies includes crashing. So mountain biking, computer security, flight simulators, and recently drones. There's a lot of crashing there. I don't know about this. Okay, so mountain biking and ants. What do ants have to do with mountain biking? There's lots of gadgets, lots of equipment involved in sports, involved in mountain biking and in cycling in general. And old school speedometers got replaced by fairly powerful computers that talk to various sensors like speed sensors, power meters, heart rate monitors, etc., and also talk to mobile phones or even your PC. And here is where ANT came in the picture, because ANT is a protocol that these devices speak. It is not just used by sports equipment, but weight scales, blood pressure monitors, or there is even a chat application that uses it to create mesh network on Android. It's called FireChat. So in this talk, I will introduce you to ANT, ANT+, and the NTFS protocols, and I'll show you some protocol-level design errors, and after that, some implementation errors in various Garmin devices. So, ANT. ANT is a wireless protocol created by Dynastream, and it is designed for low-power devices. You can create any kind of network topologies, and the participants are called nodes. There are slave and master nodes, and these nodes are communicating via mutually established channels. Channels are defined by lots and lots of properties like frequency or the channel ID. But the most important for us from a security standpoint is the network ID, because it contains an 8-byte long number called network key, which according to Dynastream is a security measure. It's a security measure because only nodes with the same network key can communicate with each other. It sounds good, but there are some problems. Network keys are managed by Dynastream, and if you want a network key for yourself, then you have to purchase one from Dynastream. And if you use an invalid network key, then the protocol stack will just default to the public key, which is public. You can download it from Dynastream's webpage. There's another problem with the network key. It is being that the majority of devices that use ANT actually use ANT+ or NTFS, and these two protocols have their own network key, and these network keys are also public. They can also be downloaded from Dynastream. So it's not much of a security measure because everybody knows those keys. Okay, other security measures in AND. There's a pairing bit. It works like this. Two nodes can communicate with each other only if the pairing bit is the same for the two nodes. So it does not have to be on, it just has to be the same on two nodes. This is fairly easy to circumvent because you can open two channels, one with the pairing bit off and the other with the pairing bit on, and one of these channels will succeed. I have first noticed that there's something fishy with this pairing bit when I came home from a mountain bike trip and realized that there are some heart rate data on my charts, despite I don't have a heart rate monitor. So it must have picked it up from another cyclist or something like that. Okay, I'm going to show you how easy it is to spoof and sensor data. I'm just going to set up my Freeton XT to use a power meter, and I'm going to use Simulant Plus, which is a software released by Dynastream to simulate a power sensor. I'm just creating the power sensor, setting a sensor data value that it will transmit, turn it on, and the watch should just pick up that signal and display that value, and yeah, it did. So without any pairing, it is this simple to spoof and sensor data. Okay, back to and security measures. There are these things called inclusion-exclusion list and white blacklist. They are essentially the same, one for the slave nodes, the other for the master nodes. They could be useful, but there's a problem with them. They are only available on fairly recent AND chips, so none of my Garmin devices can use these features. Okay, another security measure, AND channels can be encrypted with AES-CTR, but there are some problems with these too. You can't use them with shared channels, which makes it harder to implement it to have, for example, one bike computer with multiple sensors. And also, it requires advanced burst data mode, which is highly energy inefficient, and it's kind of a problem with low energy devices. So these are problems, but these have another bigger problem too. Encryption can't be used with AND+. If you use encryption, then you are not AND+ compliant, and you can't interoperate with other AND+ devices. Okay, so I've mentioned this AND+ several times already, but I did not tell you what it is. It's a protocol built on top of AND, and it basically just specifies so-called device profiles. So there's a device profile for speed sensors, a device profile for heart rate monitors, and so on and so on. These device profiles are managed by Dynastream, and they basically just govern some characteristics of the AND connection, like frequency, channel period, and data formats. A few examples of these device profiles. This is a bicycle rear view radar that uses the radar and the light device profiles, a dropper seat post that uses the seat post device profile, a bicycle headlight, obviously the light profile, and the blood pressure monitor that uses the blood pressure device profile. Okay, one of these device profiles is called sync, and it allows you to collect and transfer sensor data in the form of FIT files. So FIT is basically a file system. Yep, a file system. It's the file system file format for NTFS. The files are fairly simple. They have a 14 bytes header, some data records, and the 2 bytes CRC. And all data records have their own records header. It's a 1 byte header, and some record content. It can be anything really. So they store recorded tracks, your settings, your name, etc. in these FIT files. The reason I'm talking about FIT files is that my first attempt to hack my FreeTNXT was to try to find some memory corruption vulnerabilities in the firmware, and I did that by fuzzing the FIT SDK with AFL, and I did get some crashes, but they all seemed non-exploitable. I've tried to upload them to my FreeTNXT nevertheless, because I was hoping for some crash dumps or crash logs or some useful information, but I did not get either, so I got nothing. The watch did not crash. And this got me thinking, the ANT protocol stack became unavailable for a few minutes, and that got me thinking that maybe the ANT protocol stack, the NTFS protocol stack, is implemented in the ANT chip and not the actual Garmin firmware. So I have to explore this further. It might be interesting. Okay, back to NTFS. According to Dynastream, NTFS is a secure and reliable file transfer protocol built on top of ANT. If you Google Garmin plus ANT, then you will find some rants on various forums about how reliable this stuff is, and I do question the security. There are two major security features according to Dynastream. One is the built-in encryption. So you can encrypt your files, and they are also encrypted while on the air. It sounds nice, but I've seen some NTFS implementations, but I did not see anyone that uses this encryption feature. The other security measure in NTFS is that it employs multiple authentication mechanisms. We'll see about them. There are three authentication mechanisms, the first being the pass-through mode. It's not really an authentication mechanism because it works like this. The host just asks the client if it can connect, and the client just says, yes, why not? So no information needed to connect. I don't know why they did implement this, maybe for some testing purposes, but the important thing is that it is there and you can use it. The second authentication mechanism is called pairing mode. Don't confuse this with the ANT pairing bit. It's an entirely different concept. It requires user interaction. The host sends a serial number and a friendly name to the client. The client device displays this information to the user, and the user can decide if she accepts the connection or not. If the user accepts the connection, then a passkey is sent from the client to the host. The host stores this passkey and uses it for any further connections. So this pairing has to be only once. Okay, what's wrong with pairing mode? Obviously, if you are a malicious host, then you can send any serial numbers or any friendly names to a client, so you can maybe get the user to accept the connection. This is one way to attack pairing mode. The other is that after a successful pairing, the passkey is sent from client to host, and it can be sniffed. How do we sniff ANT? The ANT chips that the majority of these devices use are NRF24 AP1 and AP2, and these are based on the very well-known NRF24L01 Plus chips. So they work in the 2.4 gigahertz ISM band. They have a 1 megabits per secundum on-air data rate. They use GFS key modulation, but the actual packet format is not really clear from the documentations. One of the papers mentioned enhanced shock bursts, so I just went with that. But I only had an RTL SDR, which is not capable of sniffing 2.4 gigahertz. But luckily, I found this blog post where this guy sniffs NRF24L01 packets with an RTL SDR and an MMDS down converter. So I ordered an MMDS down converter, set this all up, and try to decode RTL FM output as enhanced shock burst packets. It seemed to almost work, but every byte was the double of the expected. So either they are very dumb and they use a brand new, highly sophisticated encryption algorithm where they just multiply the plain text with 2. I've seen some pretty dumb shit from developers, but this would have been a bit much of a stretch, so I just went with another idea that the documentation slide and the packet format is not really enhanced shock burst. I started reading about enhanced shock burst, and surprise, surprise, it turned out that there is a shock burst protocol. The difference between the two is a 9-bit field called packet control field, and it's being 9 bits, so it can happen that if you try to interpret a shock burst packet as an enhanced shock burst packet, that there is a 1-bit left shift, which is multiplying with 2. So it seemed a reasonable solution, so I implemented shock burst decoding. I've implemented it as a C program, and which outputs hex pairs, and I've also written an ntether.py which interprets these hex pairs as NTFS packets. This worked nicely as a proof of concept, but I wanted something cleaner, so I've implemented these functionalities in Potosphere as 2 Potosphere blocks. If you don't know Potosphere, it's very similar to GNU Radio Companion. I just like to use it more. Okay, I have a video about this too. So this is the hardware, the MMDS down converter, and the RTL SDR. And I'm using a virtual machine with 2 anti-USB sticks here. One for the NTFS host and the other for the NTFS client. So there will be a host and a client on the same machine, and they will talk to each other. And we are going to sniff them using these POTOS blocks. Yeah, it's starting. So this one is the shock burst decoder and the NTFS decoder. I'm opening the client channel, the client beacons. We can already see the client beacons. And I will just try to search for the client on the host. And when the host finds the client, it sends a link command which changes the communication frequency. And this is why this feedback from the NTFS decoder to the SDR source is there, so it can change the SDR source's frequency. Okay, there are some serial number request responses, some more beacons, and when we try to download the directory listing, it's also a file. There's download request response packet, and this is actually the directory listing. It's not yet parsed. And this is where my USB stack failed me. It did not like all those data. Okay, so we've talked about two authentication mechanisms so far. The last one is the passkey mode. Passkeys are up to 255 bytes long, so brute forcing them is impractical. But as I've told you earlier, after a successful pairing, the host remembers the passkey, and the passkeys are stored in a directory structure. So there's a client serial number and the corresponding passkey, another serial number, another passkey, and so on and so on. And when the host encounters a client with a known serial, then it tries to authenticate with the stored passkey. This whole process could be man-in-the-middled by first posing as NFS host, acquiring the client serial number, then spoofing this serial number, acting as a client. The host will send us the passkey, and we can then use this passkey to authenticate to the client. I've tried to use NFS PC tools for this, and I've expected to find the passkey in the debug logs, but the actual passkey algorithm made it impossible because the host checks the passkey length, and if it does not match the stored length, then it aborts the authentication process. But since we are the host in step 2, we can patch this functionality and still get the passkey. I found out that the ant wrappedlib.dll contains the code path for this functionality. I've almost started to binary patch it, but noticed just in time that Dynastream actually released the source codes, so I just have to modify the C code and recompile the DLL to do this attack. So as first step, we are going to pose as a host and get the client serial number. I'm just setting up some things here, okay? And I've also used my FreeTNXT for this. The host is searching for the client, and we should get the client information soon. Yeah, it's not the fastest protocol, but we've got the device ID, which will be needed. So with that device ID, we can start an NFS PC client and impersonate that client. Okay, I'm just skipping some parts. Yep, so started the client, and I'm starting Garmin Express on my other computer, where this FreeTNXT is already registered. And because Garmin Express thinks that this NFS PC client is this watch, it will send the passkey to it. And we can see it in the debug logs. Okay, opening the log files. And these lines with starting with HCK, those are the patched in stuff. There's the passkey length and the passkey itself. And now we can use that passkey to authenticate to the watch and download the files from it. Yeah, I'm just copy-pasting that passkey. And starting the channel, starting searching for the client, and you can see that there is no user interaction on the client side. Spassky, it succeeded, and we can download the directory structure without any user interaction from the client side. So this is how this man-in-the-middle attack works. Okay, so this was the part about the design errors, the protocol level errors. So I just recap it and ask the question, is it all crap? And yeah, I have to say it pretty much is. It is possible to create a secure end connection, but you have to purchase your own network key from Dynastream. You can't use End+, so you won't be able to interoperate with other End+ devices. And also you have to use fairly recent End chips. So moving on to implementation errors. I'm going to show you implementation errors in Garmin devices simply because I have those Garmin devices because of mountain biking. So I don't have anything against Garmin. I just use their stuff. Okay. The first authentication method was the pass-through mode. And I've assumed that it is only used for testing or something like that. But of course, I've implemented it in a little proof of concept script called hackend.py, and I've tried it with both my Garmin Fleet XT and with my Vivo Fit, and it worked. So it means that you can access all the files on these devices without any authentication, with just using the pass-through mode. I'm showing you this by downloading the directory structure from a Vivo Fit using this pass-through mode, and yeah, it succeeded. Okay. Oh, sorry. If this was not enough, there's another mode which you can access, I assume, all Garmin devices. I could access every Garmin devices I've tried with this. And it works like this. I'm sorry. Okay, so I'm just confused the slides. Okay, so there's a feature called OTA firmware updates. There are lots and lots of devices that don't even have any other communication method than AND, so firmware updates have to be done via AND. The firmware update method is pretty well documented by Dynastream, but of course Garmin does not use this method. So I've started to reverse engineer the Garmin Express services to learn how it actually works. But I've got distracted. I've got distracted by these two methods. The first being compute factory paired device pass key, and the other being has factory paired device pass key. I've assumed that they are using these for bundled devices, so you can buy a watch and the heart rate monitor together, and they are factory paired, so you don't have to do that. But of course, I've implemented this compute factory paired device pass key method in hackend.py too, and I've tried it with the Fleet XT and the Vivo Fit, and it worked in both cases. So it basically computes a pass key from the device's serial number and uses it for connection. The serial number, as I've shown you earlier, can be obtained by posing as a host, and we are posing as a host because we are trying to download files from a client. And it worked. You can see that here's the device ID, the serial number, and the computed passkey. So this is another method to access Garmin devices. One more thing about this is that you don't have to pose as a host to get the serial number because they are printed on the device itself and also on the packaging. So you can just walk into Best Buy, write down a lot of serial numbers, and then hack the devices later. Okay, so I've started talking about over-the-air firmware updates. And it works like this with Garmin gadgets. The firmware updates are RGN files which are so-called region-wrapped firmware files. They have to be unwrapped, and this unwrapped firmware file has to be uploaded to the NTFS directory, to the first index of the NTFS directory. It's that simple. Of course, I've tried to upload firmwares that are modified, but at first I did not succeed. So it was clear that there is some firmware checking algorithm. And in the VivoFit firmware, I found two CRC16 tables and two CRC16 functions. But it turned out that these were not used for firmware integrity checking, but finding them was still useful. And I love this about hacking, that there's a lot of scenarios where you go down one road and you expect some result, and you don't get that result, but what you get is still useful. So what was useful about this is these functions used direct addresses to the CRC16 tables, which made it possible to deduce on what address the firmware is actually loaded in memory. So it was useful for me. But the actual firmware integrity checking algorithm was much, much simpler than CRC16. There's just a requirement that the sum of all bytes have to be 0. It's fairly easy to calculate. So I've also implemented this feature in hackant.py, and I show you this by upgrading the VivoFit firmware after slightly modifying it. So first, unwrapping the firmware file, modifying it. I'm just going to replace the string sleep with another string hacked. Okay, saving the file, fixing the CRC, and uploading it to the device using hackant.py. Uploading it to the first index as a device file type. And as you can see, in the case of the VivoFit, it actually requires user interaction because the ANT protocol stack is off by default for the reason of preserving battery. But you can do this with the free 10XT, and it requires no user interaction. I'm using the VivoFit for this demo because it's a much simpler device and a much cheaper device, so it's not that much of pain if I break it somehow. Okay, so the firmware update succeeded, and now we try to enter sleep mode, and it should display hacked instead of sleep. And yeah, it does. So, thanks. Thanks. Whoa. Stop. Okay, so it was a very little modification, but you can imagine that there's a lot of stuff that can be done with this. Okay, I have one other thing to show you, and it is not strictly Ant related, but I found this issue while doing this research. In the VivoFit firmware, I have found an XML string, which kind of looked like some kind of device descriptor file. And I've tried to reverse engineer the Garmin Connect Android application to see what this file is. And I have found some functions that download this file and process this file from the device. A few years ago, I've reported some XXC vulnerabilities to Garmin. At least I tried to report them. Got no response. So the first thought was that maybe this is XXC able too. I was thinking about attacking my phone via a modified firmware VivoFit using XXE. So I've just replaced the XML string with an XXE stub that uses a external parameter entity to connect back to one of my servers, uploaded this firmware to the VivoFit and tried to connect it to my phone. Okay. And yeah, it's I'm going to disappoint you guys here because I don't have a video or a live demo of this. I've just have these screenshots. But the important thing is that when I try to connect my VivoFit to my mobile phone, a connection came to my server. But the connection did not come from my mobile phone. It was not my IP address, but after looking it up, it was a Garmin IP address. So what's happened is the mobile phone downloaded the XML file from the VivoFit and sent it directly without any modifications to a Garmin service, and the Garmin service was susceptible to XXC. And you can see it's even Java, so you can do directory listings and stuff like that. And I think it's a really complicated but really nice way to find a vulnerability like this in a major vendor's internet accessible services. Okay, so this was the last thing I wanted to show you guys. Small summary. Ant is bad. I'm using it because I have these devices, but it's really easy to sniff, really easy to man in the middle. The security features are not really security features. They are fairly easy to circumvent. So it is really easy to steal your track data, your settings data, or your files that are on these devices. Or even it is even possible to update, to replace the firmware on your device without your knowledge remotely. Okay, so if you have any questions, you can contact me in these channels, and the scripts and tools I've mentioned that I have written will be available on my GitHub later today. Thank you very much for listening to this talk. Bye-bye.